Welcome back to part 2 of implicit differentiation. Hopefully you have already played around with the warm-up problem where you find the slope of a tangent line on an ellipse. If not, go and try that problem and then come back and we're going to look at an alternative way to approach those equations that are written in implicit form. You may recognize these three problems presented at the top of the screen. We first encountered them when we learned what we call the chain rule. The first problem is just a power rule problem. We have found that the shortcut to calculating the rate that x squared changes as x changes is that we multiply by the current exponent and then subtract 1 from the exponent. The second problem is almost identical. The only difference is that our variable x has been changed into a variable u in both cases. And so the problem works identically. It doesn't matter if our problem is using x's or u's. We can apply the power rule to solve it. Now the third problem is distinctly different, and that's because one of our variables has been changed to a u, the variable in our function. But the other variable, the variable that we're finding the rate in terms of, has not changed. It's still an x. And we solved this using what's known as the chain rule. We can still apply the power rule to our function, 2u. But since we don't know u in terms of x, we have to add a chain where we multiply the rate that u changes as x is changing. And that's the way we can calculate that particular rate of change. So looking at a couple of example problems that help us to kind of illustrate and highlight this idea. First problem, the derivative of 3x squared can be done with the power rule, 6x. However, our second problem is the derivative of 3y squared, and we will notice that we have changed our x into a y, but we still are trying to calculate the rate of change as x changes. So we can again still apply our power rule to 3y squared, but we're going to need to multiply using the chain rule by the rate that y changes as x changes. Doing another example, the derivative of x plus 3y. Well, this using our sum of functions rule, can be broken up into two separate derivatives. The rate that x is changing as x is changing, plus the rate that 3y is changing as x is changing. The derivative of x is just 1. The derivative of 3y is 3, but because our variables don't match, we need to use the chain rule and multiply by dy over dx. Let's try 3 more examples. The derivative in terms of t of 3s minus 5. Well, the derivative of 3s is 3, but since our variables do not match each other, we use the chain rule, ds over dt, minus 0, or 3 ds over dt. The next two problems you'll notice are almost identical. The only difference is that the first one asks us to find the derivative in terms of q, and the second one in terms of r. All that's going to change is where in the problem we have to apply the chain rule. So first step is to do the derivative of 2q. Since the variables agree with one another, our function is using the same variable as our derivative, then we just use the power rule. But in the second part of our derivative, since the variables do not match, we have to apply the chain rule. And in the second problem, the approach is almost the same, but where we apply the chain rule is going to be different. So what these exercises are meant to really drive home to us is anytime we're doing a derivative, we have to pay careful attention to the variable in the denominator of our derivative, because it tells us what variable our function should be written in terms of. And if we ever come across a case where those variables do not agree with each other, we have to apply the chain rule. This is going to give us a new way to approach our problem about the ellipse. So see if you can apply this method of doing derivatives, one where we do not isolate the y and calculate the slope of this ellipse at x equals 2. Well, now that you've had a chance to try and think about how you might approach that problem, we've got our equation 4x squared plus y squared equals 64. Previously, we turned this equation into y equals the square root of 64 minus 4x squared. And then we took the derivative of both sides of that equation. But here, we're just going to try and take the derivative of both sides in the form that it's currently in, because we're not that bothered by this y squared being on the same side of the equation as 4x squared. The left side of our equation becomes the derivative of 4x squared in terms of x plus the derivative of y squared also in terms of x, and then on the right side of our equation the derivative of 64 in terms of x. And we can just solve each one of these derivatives separately. 4x squared requires the chain rule, that's 8x, plus the derivative of y squared, we'll do the power rule, 2y, and then chain rule because our variables do not match, multiplied by the derivative of y, equals, and the derivative of a constant is 0. Now, we're trying to calculate the slope of the tangent line when x is equal to 2. Well, there is a symbol in our new equation that represents the slope of the tangent line. That's this symbol right here. This symbol means the rate that y changes as x changes. Well, we've been calling this slope since Algebra 1. So if we want to solve for the slope of this function, we should start by trying to isolate the symbol that represents slope. So let's move our 8x over to the other side, 2y, dy over dx equals negative 8x, and divide by 2y, dy over dx is equal to negative 4x over y. Now, when we solve for derivatives, we're used to getting to a place like this. What is new for us in this case is that we have both an x and we have a y. All that means, though, is when we get to the final step where we need to plug in order to calculate our slope, we just need to take into account both the x and the y coordinate. Now, our problem only gives us an x coordinate. We know that x is equal to 2. But it also gives us a function, which we can simply use in order to solve for y. So we get 8 plus y, no, that's not 8, that's 16, plus y equals 64. Y is equal to 48, y squared, that is. Y is equal to plus or minus root 48. Plugging those y values into our function give us negative 4 times 2 over root 48, or negative 4 times 2 over negative root 48, giving us, hopefully you'll remember, the same two answers that we had gotten previously. Negative 2 over root 3, or 2 over negative root 3, which becomes positive.